We have three flavors of optimization problems. So let's recount what we've done so far. We have a classification where we talk about we have a local, is it a local max, a local min? Is it a saddle? So this is locally saying what's happening. And that came to the second partials test. So you want to make sure you can do the second partials test. The next thing we did is we said, well, I don't want local, I want global or absolute. Now I want to find the truly largest the function can be in some domain, or the smallest it can be. And we have a tool that does it as long as our domain is closed and bounded. And so one of the ways to recognize you're on that type of a problem is look for something closed and bounded. And for that we said, okay, it's the Santa Claus type approach. Make a list. Where are all the points where the largest or smallest could be? Once you make that list, plug everything in. Largest value, that's your max. Smallest value, that's your min. The third flavor is today. Optimization with a constraint. So our goal is that we want to optimize a function. We're going to mostly focus on a function of two variables. The same idea applies to functions of three or more. But I want to optimize f of x, y. But there's a constraint. Now by constraint we mean that not every x and y can be considered. So we're limiting the choice of x and y. And our constraint is going to take the form of function g of xy equals c. So what we have is now I'm saying, look, I want to optimize, but now I'm optimizing over a very particular set. So sort of a picture here of what you should have in mind is g of xy equals c is a curve in the plane. So g of xy equals c says on this curve, what's the largest that the value of the function f can be? Now this is different than what we talked about last time, because last time when we talked about optimization we said, well, normally we deal with an interior as well. There's no interior here. This is just the curve on the curve. And by the way, I mentioned last time that what if you have a very strange boundary? How do you handle that? And the answer is we use this technique. So this is good to know when you have unusual boundaries. All right, well, so we have these problems, and again, these problems are pretty easy to identify. You have a function you're trying to optimize, and there's a constraint. So you look for a function which is a constraint, or you look for things that say, given that, satisfying, things like that. Now, what's our approach? Well, the philosophy is pretty easy. See, if I'm at an optimum value, an optimum is just a way of saying a minimum or a maximum. If I'm at an optimum value, I don't want to move because I'm optimized. So somehow we can say, all right, well, let's figure out when we would want to move. Because if I know when I do want to move, that rules those points out. All right, so how do we make a decision? Well, suppose I'm at a point. So here's my point. I'll go right here. And then I'm going to blow this up. Conveniently already done for me. And I'm at this point. Well, remember here, this bluish line is our constraint. So when I talk about moving, I'm going to move along this blue line. So I'm going to either move slightly in that direction or move slightly in that direction. So that's the kind of perturbation I can need. Now, on a side note, notice how we're talking about zooming in. So when I look at this point here, it's pretty flat nearby. That's a thing to keep in mind. Okay, now, so we have our motion. So the motion along the curve is essentially we move in the direction of the tangent, one way or the other. The next idea is the function f. Now, if I want to understand the behavior at a function, oftentimes when we were in single variable calculus, we'd say, look at the derivative. Well, we're in multivariable calculus. So now we say, don't look at the derivative. We say, look at the gradient. Yeah. The gradient is acting like the same thing about the derivative. It's giving us information about how things are changing. So let's suppose I look at the gradient vector and I'll suppose it comes off at some angle like so. Now, given that this is my picture, and let's assume that the picture is accurate, which is to say that this angle theta is very acute. It's an acute angle. Is this going to be an optimum value? In other words, is that point on the curve G a point that I want to stay at? And the answer is no. But why? So here's the idea. I can just think about a very, very small change. So oftentimes in calculus we come down to saying, think of the small. What happens if I make a small change? So if I make a small change, it's basically saying just move in this direction. Move in this tangential direction. Now the question is, does my function go up or down? Well, if I want to know if my function is going up or down, it's the same as asking, what's the directional derivative? Is it positive or negative? Well, how do you figure out directional derivatives? Use the gradient dot the direction. Now, if you remember how you take a dot product, the gradient dot of the direction vector is the magnitude of the gradient times cosine theta. So when theta is an acute angle here, cosine theta is positive, which means if I perturb locally going in that direction, it's going to be a positive directional derivative. I'm going up. So I can't be at a minimum, because going that way, I increase. Can I be at a maximum?
No.
No. Why? Because I can go the other direction. And the other direction, again, think locally, because this is now an obtuse angle. If I think about the directional derivative, it would have a cosine of an obtuse angle, which is negative, which means that the function f would decrease if I just did a slight perturbation, which means I can get even smaller. So I can't be at a max or a min if my angle here is not right. Well, what's the right kind of angle to have? The right angle. It's even in the name. This is the right angle to have. So, if I am at an optimum, it has to be the case that the gradient of my function f has to be perpendicular. All right, so that's the big idea. Now, what else do we know? Well, that's what we just said. The gradient has to be perpendicular. Is there anything else which is also going to be perpendicular to this curve G? Now, this might test your memory skills.
The opposite of the gradient? The gradient going in the other way?
Well, yeah, but that's still the gradient up to a multiple. Some other thing, not gradient of f. Well, the answer is the gradient of G. The gradient of G is also perpendicular to G of x, y equals c. This comes from the idea that G of x, y equals c is a level curve. Level curve is that when you slice it. And gradients are perpendicular to level curves. So I have that the gradient of f is going to be perpendicular. And I have that the gradient of G is also going to be perpendicular. Maybe it points in a slightly different direction, but it's perpendicular. Well, if they're both perpendicular to the original curve, what does that tell you about these two vectors? They're the same up to a constant. Another way of saying it is that they're parallel. So, we have the following. We'll go ahead and just say it all. If we are at an optimum, the gradients are multiples of each other. So there's some constant called lambda, and we call this the Lagrange multiplier. So this is sometimes called the Lagrange multiplier method. So we say that the gradients have to be parallel. In other words, they have to be multiples of each other. And in addition to that, we have to satisfy the constraint. So we now have a system of equations. And if you go through and you count how many equations you have and how many unknowns you have, you'll discover it's the right number. So let's talk about it. If I'm looking at this system of equations, assuming I'm in my setting where I have functions of two variables, I have one equation from the g equals c. Gradient of f equals lambda gradient of g. Well, gradients you split into its component forms. So you're going to get an entry from the partial derivative with respect to x and an entry from the partial derivative with respect to y. So there's actually two equations embedded into this one single expression, which means I have three equations there. And how many unknowns do I have? Well, I have three unknowns: x, y, and lambda. Okay, well that's the right number. We like to have the same number of equations as we have unknowns, and now we solve. So how do we do it? Okay, this is the entire process written down. So step number one, you set up this system of equations. Now oftentimes we don't write gradient of f equals lambda gradient g, we go into the partial derivatives. So gradient of f equals lambda gradient of g becomes partial f partial x equals lambda partial g partial x, and partial f partial y equals lambda partial g partial y. All right, so we set up our systems of equations, and of course we still have their g equals c. Now, once we set it up, we find all the points which solve the system of equations. The problem with that step is it makes it sound easy. This is the hard part. How do you find these points? Well, my advice to you is, when in doubt, solve for lambda. Now, what do I mean by that? Go to your equations involving lambda and just say, write it as lambda equals something. So you're going to get two of them. Lambda equals something from the derivatives with respect to x. Lambda equals something from the derivatives with respect to y. Now, those both equal each other. And that gives you a new relationship for x and y. You'll have two relationships for x and y, and then you can solve for x and y. So that's my advice. If you have no idea how to proceed, solve for lambda. And the third thing is, plug in your points and interpret the results. So it's actually not a very complicated process. You just have to know how to get going. You have to know how to set up the equations, and you have to know how to find the points. And the rest are examples. So any questions before we jump into examples? All right. So let's begin. Find the maximum and minimum values for f of x, y equals y squared minus x squared. And this should say given. I don't know why it says give. That's just a weird expression to say give the function. Given 1/4 x squared plus y squared equals 1. So this is our constraint. So we're trying to optimize given our constraint. All right. So we can say, going through the process, that g of x, y is the 1/4 x squared plus y squared. So we are going to set up our system of equations. Recall, gradient of f is lambda gradient of g, and the constraint, g equals c. Well, that's going to translate into, go through here, the derivative of f with respect to x, negative 2x, equals lambda, derivative of g with respect to x, 1/2 x. Derivative of f with respect to y, 2y, is equal to lambda times the derivative of g with respect to y, just 2y. Good. And then the last equation is the constraint. 1/4 x squared plus y squared equals 1. Now, how do we proceed? Well, we can take a look at things. So let's suppose I look at this equation. 2y equals lambda 2y. What does that tell us? All right. So I've heard it tells us that lambda equals 1. Is that the answer? Now you're probably saying, he's saying that in the way that means it's not the answer. But I don't know, why not? Okay. Let's see if lambda equals 1 works. Suppose for a second lambda equals 1. It could be. All right. So lambda equals 1 is a possibility. If lambda equals 1, what does that tell you about x? Well, negative 2x equals a half x. For which values of x is that possible? 0. So that would tell us if lambda equals 1, that would imply that negative 2x equals a half x, which would imply that x equals 0. Now, we haven't used our constraint. We get 1/4 times 0 squared plus y squared equals 1. So that would imply that y squared equals 1, which would end us with the points y equals plus minus 1. And, oh boy, I'm just wandering all over the place here. 0, 1, 0, negative 1. Okay, so those are certainly points that we might care about. Now, have we missed anything? And why did we miss it? And how do we fix it? Now, I'm not saying that lambda equals 1 is invalid. Lambda could be 1. Absolutely, lambda could be 1. That would lead us to the points 0, 1, and 0, negative 1. But is there anything else that we missed? And how do we find that?
Y could be 0, so lambda the x value that it would give you.
Yeah, let's go back to the original equation here. When we said 2y equals lambda 2y, there's this natural instinct to say, look, they both have 2y on both sides. Let's divide out to cancel. It's a very natural instinct because we were trained to do that in algebra. However, there's a problem. When you're dividing to cancel, you must be ever so careful that you don't divide by 0. So you should always be careful and say, I'll never divide to cancel unless I'm 100% sure it's not 0. Well, the problem is that y could be 0. Now, you might say, well, how do I make progress in these problems if I can't divide to cancel? And the answer is, instead, and this is very fancy, move everything to one side and factor. So this can factor as 2y lambda minus 1. So you get that the lambda equals 1 is a possibility and y equals 0. So the moral is, if you can ever divide out to cancel, you can also factor out. And you should only ever divide if what you're dividing by is non-zero. So if you have like e to the x, perfectly okay to divide out by e to the x. E to the x can never be 0. Okay, so we do have to worry about the y equals 0 case. So let's do the y equals 0 case. So if I know that y equals 0, I come up here and I say, okay, well that tells me 1/4 x squared needs to be 1. What does that say about x squared? It should be 4. So what does that say about x? Plus or minus 2, which gives us the points 2, 0, negative 2, 0. So what we have is, after you set up the system of equations, you go through, you solve, you get the following list of points. So in some sense, this is similar to last time, where we're finding a list of points that satisfy the system of equations. 0, 1, 0, negative 1, 2, 0, negative 2, 0. So these points represent all the points which satisfy our constraint and also have the two gradients are parallel. So our optimum has to be at these points. So how do we figure out which one is the max and which one is the min? Yeah, we evaluate. Okay. So f at 0, 1. Well, we're going to get 1 squared minus 0 squared. That's 1. F of 0, negative 1. Negative 1 squared minus 0 squared. 1. 2, 0. 0 squared minus 2 squared, negative 4. Negative 2, 0. 0 squared minus negative 2 squared, negative 4. So what's the maximum? 1. This is the maximum it can take. What's the minimum? Negative 4. That's the minimum it can take. And we're done. We finished the problem. Now, in some sense, this seems a little bit sort of hand-wavy there, but you know, it's okay. When you're dealing with systems of equations, you sort of probe it. Say, how can I manipulate things? What can I do? This was a case where I didn't have to solve for lambda. On a side note, you might say, you know, that was a lot of work. Let me show you how to do it faster. You have this constraint here. Why not just use it? So in other words, f of xy equals y squared minus x squared. Well, why don't we just note that y squared is 1 minus 1/4 x squared? Because it's true. Y squared is 1 minus 1/4 x squared minus x squared. So that we end up with 1 minus 5/4 x squared. And you might say, okay, well, is that fair? Well, you have to throw in some other things. You can say, well, how big can x be? Well, given that x is between negative 2 and positive 2, because anything bigger than negative 2 or positive 2 can't satisfy the original condition. Okay. All right. And yeah, at this point you're like, oh, this is just old single variable calculus stuff. And our response is, yeah, we know. Yes, a lot of times you can just do substitution from the constraint, but we want you to go through the process because there are times that you can't do that. And we have some examples. I think we have one that we're going to do next time, and we'll have one in a few minutes, which again you can't do. So yes, I understand that it is possible to go through and do it in different ways by saying, let me use the constraint to reduce the number of variables. But again, we don't want you to do that. We want you to follow the process. All right, now let's do another problem. And this one is from an old final exam. We don't talk about that final exam very much in our department for pretty good reasons. And we'll see why in just a moment. So maximize. We want to maximize the value of the function 1 over x plus 1 over y subject to x plus 4y equals 1. Now, how do we know that this is a technique that we should use the Lagrange multipliers on? What are some clues? Yeah, subject to. The fact that we see two functions here, one that we're maximizing and one which is a constraint. So this maximizing, that one is going to be our f. F of xy subject to, this is our g of xy. All right, so far so good. So we set up our system of equations. Gradient of f equals lambda gradient g, and of course g equals c. So what is partial f partial x? Negative 1 over x squared is equal to lambda partial g partial x. One. Okay. Partial f partial y. Derivative of 1 over y with respect to y. Minus 1 over y squared equals lambda derivative of g with respect to y. 4. And I have the constraint x plus 4y better be 1. All right. Well, combining these two equations here, you'll notice they're almost the same. So in fact, if I were to multiply the first equation by 4, so it becomes minus 4 over x squared is lambda times 4, I say, aha, now they really are the same, so that I can combine these together to minus 4 over x squared is equal to negative 1 over y squared. Cross multiplying, we get that 4y squared equals x squared. I also got rid of the negatives. So what does that tell us about the relationship between x and y? So taking the square root of both sides, x equals 2y.
That's the value.
Or, what's the other thing that could happen? X equals negative 2y, or negative x equals 2y. So in some sense there's absolute values, but it's also just another way of saying plus or minus. This is kind of the spirit of how these problems typically go. You get two relationships, you somehow get rid of lambda, and you get simple relationships between x and y. Now let's just follow them through. So if x equals 2y, so let's see that one. If x equals 2y, we're going to get 2y plus 4y equals 1. So what does that say about y? Y is 1/6. And what does that say about x? Just twice that. 1/3. Okay, so on our list, 1/3, 1/6. All right. Now that was one option. What if x equals negative 2y? Well, then that would say that negative 2y plus 4y equals 1. What does that say about y? Y is a half. What does it say about x? 1. Oh yeah, right. Sorry, negative 1. Yes, because of the negative 2. All right. So we have 1/3, 1/6, and negative 1, 1/2. We have our list of points. If we have an optimum, it has to be at one of those 2 points. Well, what comes next? We plug them in. Okay, so remember that we're going to do 1 over x plus 1 over y. 1 over 3, well, we'll do 1 over 1 over 3. So that's going to become 3. 1 over 1 over 6 is going to become 6. So I'll put those together, that gets 9. Plug in negative 1 and a half. Well, 1 over negative 1 is negative 1. 1 over a half would be 2. Negative 1 plus 2 is 1. Okay. Now, which one's the maximum? 9. Okay, so we want to say that this is the max, right? Because it's the largest value. I'm even writing the word max, and yet my voice seems to betray that idea. But we'll write it down. What is the minimum? 1. Now, that was the question on the exam. We don't talk about this exam. Here's why. That's wrong. Now you're probably thinking, no, I'm pretty sure 9 is bigger than 1. I learned that a long time ago. It turns out that this problem had to be written in haste. And they didn't check what was going on. 9 is not a maximum, it's actually a minimum. And 1, it's not a minimum, it's actually a maximum. Now you're probably like, no, that's not how numbers work. Okay, so let me explain why you have to be careful. Let's think about what's happening. We're moving along the curve x plus 4y equals 1. Now if you were to plot this curve, it would look something along the lines of the following. That's x plus 4y equals 1. And what we found is we found a pair of points. We have a point somewhere over here. We have a point somewhere over here. And here's the thing you have to think about. What's happening to the function? Well, notice that 1 over x, 1 over y. These problems, anywhere where you get x is 0, y is 0, is a big whoops. The function is not defined. So, think about what happens. As I approach one of these points, say on this side, well, what's going to happen is that I'm going to get larger and larger. Because it's 1 over a small value. 1 over a small value. So I'm heading towards infinity in either direction. And here's 9. So if this is 9, and either direction I go, I'm going to have to eventually go towards infinity. It means 9 is at a local minimum. Similarly, if I'm coming from this direction, I'm actually going to approach negative infinity as I head off to there. And if I were to go way, way out over there, I'm going to head towards 0. So I'm going from negative infinity, I get to 1, I go to 0. That means I'm locally a minimum. Okay, so what's the moral of the story? You have to be careful. Now, oftentimes we'll just say, find it. And if we just say find it and you find a point, that's the right answer. Don't think too much. But maybe someday you won't be in a calculus class and you have to say, okay, am I at a min or a max? Well, how could we decide? Well, the answer is perturb it a little bit. And just say, well, what if I went a little bit that way or went a little bit that way? What happens to the value? Now, let me tell you what the answer is definitely not. Don't apply the second partials test. The second partials test is worthless in this setting. Now, as a reminder, when is the second partials test worthful? I guess that worthful must be a word if worthless is a word. When can you apply the second partials test? When you're at a critical point where the gradient is 0. We are not necessarily at points where the gradient is 0. So you have to be careful. The second partials test doesn't apply. If you're in doubt, just perturb. Say, well, what about this point over here? What about that point over there? Let me compare. That's how you can figure out if something truly is a local min or a local max. Most of the time, we'll give you things which are a little bit nicer behaved. Now, you might say, wait a second, why didn't you panic on the last question? Well, let's talk about that for just a second, why the last one didn't make me panic. 1/4 x squared plus y squared equals 1. Do we know what shape that is? It's almost a circle. If it was 1/4 x squared plus 1/4 y squared equals 1, it'd be a circle. It's an ellipse. It's an ellipse which is slightly longer in the x direction than it is in the y direction. You'll notice that if I look at these sets of points, they're closed and bounded. And the function is continuous. I had a continuous function, closed and bounded. It has to be the case that it achieves absolute max and absolute min. On the other hand, x plus 4y equals 1 is definitely not bounded. 1 over x plus 1 over y, definitely not continuous. So you have to be careful. All right. Now that I've shaken your faith, let's do some more. Okay. Find the points which are nearest and furthest from the origin given 7x squared plus 3xy plus 3y squared equals 25. Now, this is one which demonstrates you'd have a hard time actually solving for x or for y. Not in an impossible time, but you'd have a hard time. So this is not a, oh, I can always substitute. Well, not really. You have to be ready to use the method. What tells us that this is a Lagrange multiplier type problem? The word given. It's practically a given that if you see the word given, Lagrange multiplier. All right, so this function, 7x squared plus 3xy plus 3y squared equals 25, is that my constraint or is that what I'm trying to optimize? It's my constraint. In fact, one of the easy ways to tell is it equals a number. Okay, so here's my constraint. Now, that means that, wait, where's the other function? There is no other function. What do we have to do? We're going to make one. Isn't that exciting? We get to make a function. Ah, cool. Okay, well, let's figure out what the function is. So we got to find the points. So that's saying find the optimum. Okay. Are nearest and furthest from the origin. Now, when you see words like nearest and furthest, what type of thing do we think of? Distance. That's a distance type word. How near are you? How far are you? Okay, so we need a distance function. So we need to have the distance between the origin, which you might remember is 0, 0, and a point, which we'll call xy. Well, what's the distance between 0, 0 and xy? square root of x squared plus y squared. Well, that's pretty straightforward, except I don't like square roots. Okay, so instead of using this as our function, we're going to do an old trick. We're going to use x squared plus y squared, also known as the ignore the square root. Okay, now ignoring the square root is a pretty popular method. When can we use it? Well, if I'm trying to optimize the square root of something, if I want to make that expression big or small, I say, look at the something. When is that big or when is that small? So in other words, when I'm optimizing the square root, I just have to optimize the inside. Now the reason that I get to get away with this is because of the nature of the square root function. It's the technical phrase, monotonically increasing. But another way of saying that is it always goes up. That's what monotonically increasing means. It's always going up. So if I want to get the largest, I just say, okay, make the inside as large. If I want to get the smallest, make the inside small. Okay, so now we have our function. We have our constraint. We're ready. We're in business. All right, good. So gradient of f equals lambda gradient of g, and our constraint g equals c. So let's set it up. What is f sub x? 2x. Equals lambda. What's g sub x?
14x plus 3y.
14x plus 3y. Okay, f sub y, 2y, equals lambda g sub y, 3x plus 6y. All right, now, I don't know about you, but I'm feeling doubt. Well, what should we do if we're in doubt? Solve for lambda. Yes, that's right. When in doubt, solve for lambda. So, if I solve for lambda, I can say that 2x divided by 14x plus 3y is equal to lambda, but that's also equal to 2y divided by 3x plus 6y. Now, the very fancy thing we do is just make these equal signs really long, ignoring the lambda in the middle, and say, okay, let's work with this. Okay, so some things we can do. Well, let's just note both sides have a 2. We can go ahead and cancel the 2 before we get too far down. And I don't like fractions. It's just a weakness of mine. So if I don't like fractions, what I do is I get rid of the fractions. And the way to get rid of the fractions here, cross multiply. So I'm going to multiply the x times 3x plus 6y. Then I'm going to do the y times 14x plus 3y. So cross multiplication, we get 3x squared plus 6xy. Well, that's going to be equal to 14xy plus 3y squared. All right. Are you nervous yet? Really? Wow, you guys are very trusting. Okay. I'm nervous. Things aren't canceling. Because we're like, shouldn't everything cancel in this class? Maybe. Move everything to one side. And now we start saying, oh, please, please, you gods of algebra, please factor. Now, I just want to make it clear, there are no real gods of algebra. We've been told that we're not supposed to discuss certain topics. Politics is off the table. Religion, I'm sure, is soon to follow. Okay, but we want it to factor. Does this factor? Well, what do you think? Have we finally come to the point in class where something doesn't factor? If it were to factor, we probably would want a 3x and an x, and we would probably want a 3y and a y. Now you might say, hold on, how do you know that it's not 3x and 3y together? Well, if 3x and 3y were together, everything would have a multiple of 3. And it clearly doesn't all have multiples of 3. So this would give us 9xy. That would give us xy. Somehow we want to end up with minus 8xy. That would do it. Minus 9xy. plus xy is negative 8xy. You get minus 3y squared plus 3x squared. Wow! Cool! Someone really planned ahead on this problem. Yeah, I did. It's hard. It's hard to get these to work. Okay, now, so what does that say? Well, it says one of two things. Because we have our favorite thing. Two things are multiplying together to get 0. So, we have one of two cases. Either y is negative 3x, or x is positive 3y. That's it. Those are one of our two options. Now, what haven't we used? We haven't used the constraint. So, but I want to get you to recognize the flavor of this. We said, okay, we set up gradient of f equals lambda gradient of g. By solving for lambda, what we end up with is we end up with a new relationship between x and y. And if we're lucky, things work out. Well, when I say lucky, if we do our math right. It's the teacher's responsibility to make sure things work out. Now we come into our constraint. So let's do y equals negative 3x. So everywhere where I see y, I'm going to put negative 3x. All right, so that would be 7x squared plus 3x times negative 3x plus 3 times negative 3x squared equals 25. Well, if we work our way through this here, what do we have? We have 7x squared minus 9x squared, and this will be plus 27x squared. So 7 minus 9 plus 27 combined to give us 25x squared equals 25. What does that say about x squared? 1. So we get x equals plus or minus 1, which means that we get the following pairs of points. 1 comma negative 3, because remember y is negative 3 times x, and negative 1 comma positive 3. All right, so those are on our list of candidate points. Okay, well that's good. But that's only half, because we have another possibility. X equals 3y. So now everywhere I see an x, I'm going to put 3y. So we have 7, and then we're going to multiply that by 3y quantity squared plus 3 times 3y times y plus 3y squared, and that's going to equal 25. Now we start going through and seeing what we have. We have 7 times 9, which is 63. Then we have another 9. What are we up to? 72. Plus 3 more. 75. So 75y squared equals 25. What does that say about y squared? 1/3. So y will be plus or minus 1 over square root of 3. Okay, so that leaves us with two other points. Namely 1 over square root of 3, and then y, that's the y, x will be 3 times that, which will be square root of 3, and minus 1 over square root of 3, and then I'll have 3 times that is minus square root of 3. Okay, well what does that say? Well, we're at the point where we set up our system of equations. We solved for all possible answers. We got 4 points. Now the question is, which ones are nearest and furthest? Well, if you run through the process here, really we just have to say x squared plus y squared. You get 1 plus 9, which is 10, and 1 plus 9, which is 10. So you get 10 from here. Here you get 3 plus a third, or 3 plus a third. Well, 3 plus a third is 10/3. So the answer is that these first two, 1, negative 3, negative 1, 3, these are the points which are furthest. And the second two are the points which are closest. And that's the answer.